Welcome to In 5 Minutes. In this video clip, we will discuss Armstrong's method for FM generation. This is also very famously called indirect method for FM generation. Now, if you remember in one of the previous video clips, we had discussed how FM can be generated using phase modulator. So in that particular method, all we had to do is take the modulating signal m of t, first pass it through the integrator. So we integrate the modulating signal and then we pass that through a phase modulator PM, and obviously the phase modulator will also use the carrier signal. So if you change the phase of the carrier signal in proportion to the integration of modulating signal, then what you get on the output side is FM. So it is this principle which we have already discussed in detail along with mathematical analysis also. Based on this principle, we have the Armstrong's method, which is also called indirect method. Before we look at the detailed block diagram, so all we have to basically do is integrate the modulating signal and somehow implement the phase modulator. Now, before we see the detailed block diagram, we will go through a small analysis, mathematical analysis of Armstrong's method. No doubt that Armstrong's method is based on this indirect approach of FM generation, but it also uses one very specific way to generate FM. We will first generate narrow band FM. So we generate narrow band FM through indirect approach, and then we pass narrow band FM through group of multipliers and mixers. So if you remember, if we pass FM through multipliers and mixer, then what happens? Its modulation index increases, and not just the modulation index, we also increase delta F, which is a frequency deviation, and this will give us wide band FM at the output side. So we will first generate narrow band FM through indirect approach and pass it through multipliers and mixers. This is what we do in most of the practical FM modulators or FM generation circuits. Let's go through this very simple analysis. I'm going to consider an FM mathematical expression according to which we have FM signal can be expressed as Vc cos 2 pi Fct, where Fc is the carrier frequency, Vc is the peak amplitude, plus, remember, it is 2 pi kf integration of m of tau d tau, where tau is the dummy variable, m of t is nothing but the modulating signal. Mathematically, the limits are from minus infinity to t, but in practice, we can start from 0 because that's when the process of modulation will also start. For narrowband FM, this phase part will be a very small value. So before we go ahead, let us replace this phase part with value, let's say phi of t. So we have replaced this whole thing 2 pi kf integration with phi of t. Whenever we'll require this expression in the form of m of t, we will bring it back into picture. As of now, phi of t is this whole thing 2 pi kf into integration of the modulating signal. Now, if I expand this using the formula of cos A plus B, we get Vc cos A, which is 2 pi Fct, into cos B, which is cos of phi of t, minus it is sin A sin B, so sin 2 pi Fct into sin of phi of t. So cos A cos B minus sin A sin B is what we get. Now, we know that for narrowband FM, we have this phi of t very small. So because we are generating narrowband FM first, in that case, if phi of t is small, then I can use the approximation that cos of phi of t, if I take any angle which is very small, then cos of that angle will be almost 1 because cos of 0 is 1. So if phi of t is small, then cos of phi of t will be 1. And we also know that if the angle is small, then sine of that angle is approximately the value of the angle itself. So using this approximation, we get Vfmt equal to Vc cos phi of t is almost 1. So we get cos of 2 pi Fct alone minus Vc. I'll write this term first. Sine of phi of t is phi of t. And then I'll just mention sine of 2 pi Fct. So this is what we have to basically generate in the form of narrowband FM.